Welcome to clickmyprojects.com. Here we discuss about a built-in repair analyzer with optimal repair rate for bad-oriented memories. State-of-the-art system on chip typically devote a large percentage of chip area to various kinds of memory cores. According to the International Roadmap for Semiconductors, the percentage of memory in SoCs will continue to increase rapidly. At the same time, the shrinking features sizes will lead to increasing parameters, variabilities, and a high susceptibility to defects. As memories are traditionally designed with more aggressive design rules than logic cores, they play a crucial role for the yield and reliability of a SoC. Embedding the necessary infrastructure for the built-in self-test analysis is essential to achieve acceptable yields and the guarantee of satisfactory availability in the field. Memory reply on spare events at different levels of the design hierarchically. Faults can be compensated with redundant cells, words, rows, columns, or even a complete memory block can be replaced. Adapting the techniques to a fully built-in repair analyzer poses two problems. Firstly, most of the search strategies rely on a complete failure bitmap. Secondly, the data structure to organize the search can grow very low. To overcome these problems, most approaches for built-in repair analysis either follow only very simple search strategies or they rely on divide and conquer technique. Divide and conquer strategies addresses both the memory itself and the failure bitmap, which is replaced by the local failure bitmap. This paper presents a built-in self-analyzer with the optimal repair rate for memory arrays with redundancy. The proposed method requires only a single test even in the worst case. By performing the and must repair analysis on the fly during the test, it selectively stores fault address and the finally analyze to find a solution is performed on the stored fault addresses. By performing the must repair analysis on the fly during the test, it selectively stores faulty addresses and the finally analysis to find a solution is performed on the stored fault addresses. To enumerate all possible solutions, existing techniques use depth first search using a stack and a finite state machine. Instead, we propose a new algorithm and its combination circuit implementation. Since our formulation for the circuit allows us to use the parallel prefix algorithm, it can be configured in various ways to meet area and the time requirements. Now I am going to explain system flow diagram of our project. In the first stage, we initialize the input addresses by giving input address bits to input register. Then check the conditions whether it was satisfied to extracting the signature level or not. After that, for each and every iterations, it separated the input address bits to form as a separate register and checking whether the input signature level is conditions satisfied to zeros or 1 conditions. If it is set to 0, then it gone to extraction bit states. Else, if the condition was satisfied to 1, then it's checking whether the bits are end of the bit or not. If the end of the bit is not satisfied, then it gone to extract bits states. So finally, up to the overall end of the bits of input address, then it's checking the conditions whether it was faulty conditions or not. That is, whether the signature extracted output is set to faulty or not conditions. If it was set to faulty conditions, then check the point addresses, which is fed in the CAM register. After the faulty cases was matching, it was fed to the CAM register and the indexes was stored in the separate register as row and column. After collecting the faulty addresses from CAM memories, then these faulty addresses were fed to the solver stage. In the solver stage, a checking whether the conditions are matching to faulty libraries or not. If the faulty libraries are matching to the internal register, then that relevant output will be fed output. Yes, new faults can be registered in the library in solver states. If the input address is not in faulty cases, then this register address was passed to the out register and loaded into the memory. Now I am going to explain running procedure of our project. In the first stage, we display the RTL schematic diagram and the technology schematic diagram and checking the any errors and warnings by using check syntax error. In the first stage, we select the implementation option and select our main function. Then click check syntax and right click it and click run option. It will check the internal errors and warnings. If there are any details present in the programmings, it will be displayed in the console window. The checking each and every lines in the programming line and displays the total number of warnings and errors. If there is no any warnings or errors, it will be displayed as tick option. Then we can view the RTL schematic diagram by right click it and click run option. The RTL schematic diagram displays logical designs of the programming language. Logical diagrams may be AND operations or XOR operations. That's like this is a HDL synthesized result. Here, this is our list of components. Now click add and click create schematic option. This is our overall block diagrams. In this, input pins are clock, enable, LFSR data in and reset option. And output is the result and signature output. And here, clock is for clock inputs and enable is to set the total overall operation as to enable. And reset is to reset the overall operations. LFSR data in is set fit to give the signature options to make the extracted bits from this operation. Result gets the relevance output. If there is in faulty addresses, the fault matching libraries will be displayed. Signature output gives the result of input LFSR data signature. We can view the internal structure of the block diagram by double click it in. This is our overall structure of the operation. We can view the technology schematic by right click it and click run option. Now add and click create schematic. In the technology schematic diagram, we can view LUTs and flip-flop structures. For any other lines which is fed to that is set as a buffer. Now we can view the timing diagrams of our project. Now select simulation option and expand the design utilities. Select our main behavioral. Now select simulate behavioral model and right click it and click run option. This will display the timing diagrams of our proposed system. Here we using iSim simulator to display the timing diagrams. This will provide a GUI options which are displayed in the console window. The timing diagrams will display the input and output pins and the internal structure signal operations. Now I give the input for clock reset, LFSR data in and enable option. Now right click it and click force constant. In the force to value I set initial clock as set to 0. and set the reset condition as to 1. Right click it, LFS of data in and force constant set as 1. And enable is also set as 1. Run for specified from the toolbar. Now I give clock input as 1 and give the input as 1. In this stage, this will provide the reset conditions. Now set the reset as 0. After that, change the clock period. Now click Run option. Now it just change only the clock periods. For each and every clock cycle, this to end data will be changed. The clock periods mentioned here is that one clock period has 0 and 1 combination. So for each and every clock cycle, this to end data will be fed as an input. For the input addresses, we extract the signature at certain timing. Here it will shows the signature and result for the relevancies which are in faulty cases. So this will display for the first input address. This is the input first address and this is the signature of that input first and their relevance result. If the given input address is in faulty cases, result is set to that relevance address from solver library. If not, in faulty cases, result output will be set to 0. So for each and every clock pulse, we use the input. This input will be set to 0 and 1 condition. So for each and every cycle, input addresses will be fed as an input and the signatures and faulty cases will be extracted. Just like each and every clock cycle, changes will be done. Finally, this address from result will be saved as an output register. This is our final address. Thus we extract the faulty cases and non-faulty cases by using the signature level and find the relevance data which are produced in the library and fed it in result variable. Thank you.